All right, we're in our last segment of section 6.3 diagonalization from the textbook Linear Algebra Done Openly. And as you might be able to notice, the title of this video is called The Whole Enchilada. And this really kind of summarizes a lot of the principles that we have seen when it comes to the eigentheory we're developing in chapter 6. So we've seen previously what we mean to diagonalize a matrix, and so what we're asking to do right now is, given this 3 by 3 matrix you see in front of you, A, we want to diagonalize it if possible. At the end of the last segment, we kind of talked about there might be situations where you can't diagonalize a matrix because you don't have an eigenbasis, you don't have enough independent eigenvectors. So how does one determine if you can diagonalize it? And if you can, how does one actually do it? We're going to do all the pieces necessary in this exercise right here. So it's going to take a while. Because first of all, we don't even know what the eigenvalues are, what the eigenvectors are. To diagonalize it, what we need to do is we need to find some matrices P, D, P inverse, where D is a diagonal matrix, P is a non-singular matrix, and P is its inverse. So the first thing that you want to do is you want to look for this diagonal matrix, which requires we find the eigenvalues. So we want to find the eigenvalues for our matrix. And for our purposes, we're going to look for the eigenvalues by considering the characteristic polynomial. Remember, the characteristic polynomial is the determinant of a minus lambda I, where I is the identity matrix. You can see that right here. And so this is a 3 by 3 determinant. And so if we're just going to do cofactor expansion. There might be other strategies of computing it, but just for the sake of simplicity in terms of strategy, we'll just cofactor expand this. And we're going to cofactor expand across the first row, right? So if you look at the first minor, that's the one associated to 1 minus lambda. You see this right here. This comes from taking away the first row and first column. Then the next one, we're going to get a negative 3 because, again, our cofactors would look like negative plus negative right here. So we're going to get a negative 3, and we expand across the first row. And so we're going to kill off the second column this time. You get the minor there. And then for the last one, we're going to do plus 3 again. Take away the first row, last column, you get your minor right there. These are each 2 by 2 minors left. So for the next bit, we'll take the sort of the cross product there, product of diagonals minus the diagonals there. You're going to get, for this first one, 5 minus lambda times 1 minus lambda minus 3 times 3, which is a 9. You make sure you times all of that by 1 minus lambda because this sits out in front. Then we do the next part, negative 3 sits in front. What's the 2 by 2 determinant? You're going to get negative 3 times 1 minus lambda right there. And then negative 3 times 3, that's a negative 9, but you're subtracting, so you get a plus 9. And then same thing for the last one. Negative 3 times 3 is a negative 9. And negative 5 negative lambda times 3, you'll get 3 times 5 plus lambda. It's because it's you get a negative there, double negative. So they cancel out. And so this line right below, which you see right here, this gives us what happens when we expand all the determinants. All right, there's an argument there, but we did it. Great. Now, the reason we want to find the characteristic polynomial is we want to find the roots of this thing. And so we're going to have to try to algebraically simplify this beast. This will involve some foiling of some kind. So negative 5 on the 1 on the negative lambda on the 1 on the negative lambda. So there's a FOIL process that happens right there. Let's see, is that actually what I did here in my notes? Actually, no, I take that back. What I did is I distributed the 1 minus lambda onto these two parts right here. So since we already had a 1 minus lambda and a 1 minus lambda, I was just utilizing that to get a square right there. So you get 9 times 1 minus lambda. Here, if you distribute the negative 3 and negative 3 gives us a 9. If you distribute onto the 9, you'll get a negative 27, like so. And then distribute the 3 onto the negative 9, that's a negative 27 again. And then distribute it onto the 3 right here, you'll get another 9. So distribute all those coefficients that came from the cofactor expansion. I'm hesitating to multiply this thing out right now, and I'm practicing what in computer science we might sometimes call lazy evaluation. Right? It sounds like a lazy thing to do, as the name suggests, but I'm actually postponing multiplying out hard problems to see if I actually need to do so. Because it takes effort to compute it, and if I don't need to, I don't want to. So we're going to see if there's any benefit of waiting. So you'll notice that in our expansion, we have a 9 times 1 minus lambda and a 9 times 1 minus lambda. Those are like terms. We can add them together and get an 18 times 1 minus lambda. I kind of like that. The 27s combine to give us a negative 54, and there's not a whole lot to do with that yet. So let's see what we can do in the next stage right here. So we want to combine some more like terms. What is available to us? Well, what's going to happen here is you can actually distribute. You can distribute the 9 right here. 9 times 5 is 45, right? Let's write that down there. So you're going to get a 45, and then you're going to get 9 lambda right there. And so you'll notice that if you combined the 54 and the 45, that's going to end up with a negative 9. So you look at this negative 9 plus 9 lambda. If you factor out a negative 9 from that, you get 1 minus lambda right here. Again, I kind of hid some of the details there. Apologies for that. But that's might feel like a cheap shot. That's where that comes from. And the reason I'm doing this is, again, to try to make some of the future calculations a little bit easier. You'll notice we now have a 18 times 1 minus lambda. We have a negative 9 times 1 minus lambda. Those combine to give me a 9 times 1 minus lambda. And then at this point, we should notice that everything is divisible by 1 minus lambda. We factor it out again, and we end up with x plus lambda times negative 1 plus lambda plus a 9 right there. And so now we've reached a point where we can't avoid the FOIL any longer. But now we never had to square the 1 minus lambda. We can distribute all those jazz things. You're going to end up with a 5 times negative 1, which is a negative 5, plus the 9. That should give you a 4. You're going to get a 5 times lambda. You're going to get a lambda times negative 1. That combines to give you 4 lambda right here. And then lambda times lambda is a lambda squared. We get something like this. So you get 4 plus 4 lambda plus lambda squared. And we do want to factor this thing after all. This will factor as lambda plus 2 quantities squared. And then there's a negative sign sitting in front of everything. Oh my goodness. That was a very, very, very challenging algebraic problem. That was just about factoring that thing. And I took some steps along the way to simplify the factorization. And that's honestly because I kind of knew how I was going to factor while I was going around along the way. If I had no idea of how this thing would factor, this would have been very, very intimidating. I want to mention that in practice, when one is trying to find the eigenvalues through the characteristic polynomial, typically this is done with a computer. A computer calculates the characteristic polynomial using techniques to help simplify the determinant calculations. We only did 3x3s, but determinants can get crazy very quickly. Also, once you have the actual polynomial, simplifying and factoring, that's very, very difficult, even for a computer. We probably would want to look for numerical approximations of the eigenvalues, because we're going to see that the eigenvalues here are going to be lambda equals 1 and lambda equals negative 2. The multiplicity of 1 is 1, and the multiplicity of negative 2 is 2, which shows up twice. These, of course, are the algebraic multiplicities. We don't know the geometric multiplicities yet. These can be very difficult to find working with this polynomial, and oftentimes a numerical approach is necessary to find the numerical approximations of the roots of this polynomial here. And so numerical analysis is deeply connected to linear algebra to help us out with things like this. But once we've factored this characteristic polynomial, we can now describe the eigenvalues. We have 1 and negative 2 twice. And so then we can construct our diagonal matrix D by putting along the diagonals those eigenvalues with their algebraic multiplicities, 1, negative 2, negative 2. It doesn't matter which order you put them in, just make sure you have the correct multiplicities and that you're consistent on the next part. So this is the effort it took to get the eigenvalues. That probably is the hardest part of the problem, in my opinion, because you have to do this nonlinear calculation with the characteristic polynomial. Once you have the eigenvalues in hand, we start looking for eigenvectors. So we're going to first look for the eigenspace associated to lambda equals 1. So we take the matrix A minus I, and we're going to subtract from A 1 from each diagonal entry. And that's going to give you this matrix right here. You'll get 0, negative 6, 0 along the diagonals. Everything else is left the same. And so in terms of row reduction, I notice that everything in these matrices is divisible by 3. So divide the first, second, and third rows by 3, you get the following matrix right there: 0, 1, 1, 1, 2, 1, 1, 1, 0. I want a pivot position to be 1. I really like that. So we could switch the rows. Just take row 1 and 2. Switch those rows to get the following matrix, where we now have a 1 in the pivot position. We got to get rid of the 1 that's in the third row. So we can take row 3 minus row 1. That'll accomplish that. Then moving on to the pivot in the second position, we don't want the negative 1 below. We can get rid of that by just taking row 3 plus row 2. I also don't want the negative 2 above, so we can take row 1 minus 2 times row 2. That'll accomplish that. And then that gives us the row reduced echelon form of our matrix. We don't get a pivot in the third column. This is our RREF. All right? And so once this matrix is row reduced, we can identify a basis for the null space, because after all, the eigenspace, this right here is our eigenspace. This is the 1 eigenspace. And it's a null space of a matrix, A minus I. So we want to find a basis for that. So your basis for your null space will correspond to the free variables. We have just one free variable in the third position. And so we are going to grab these numbers right here and write their opposites. So we get a 1 for the first variable, and we get since we had a 1 right here, we're going to get a negative 1 right here. And that's exactly this vector right there. So we get our first eigenvector. 1, negative 1, 1. It forms a basis for the eigenspace, and this gives us an eigenvector we want. So as we're trying to build our matrix P, we can think of the following idea. Our matrix P, we now have the first column that's associated to 1. It's going to be 1, negative 1, 1. Well, we need 2 more columns that'll come from the eigenvalue negative 2. So we basically repeat this process, rinse and repeat. We look at the matrix A plus 2i. If we add 2 to each of the diagonal entries, we're going to get 3, 3, 3, negative 3, negative 3, negative 3, 3, 3, 3. That might be kind of easy to row reduce that one. Notice that the first and third row are identical, so you can subtract them to get 0. And then honestly, the second row is just the additive inverse of the first row. Add them to get 0 there. And since everything was divisible by 3, divide by 3 again. All right. So in this situation, that one rows reduced pretty quickly. We have a pivot in the first row, but in terms of our basis for the null space, we have 2 free variables. So that's going to give us 2 independent eigenvectors. This actually is evidence right here now that we're going to have an eigenbasis. We have free variables in the first and third position. We put those there. And so looking at the coefficients, we have a 1 right there and a 1 right there. So we write negative 1 and negative 1, which then gives us the basis for the eigenspace right here. So notice that if we're looking at the null space of A plus 2i, this right here gives us the negative 2 eigenspace of this matrix. And so we then find a basis for that, use that basis, this part right here. And so we're going to get negative 1, 1, 0, negative 1, 0, 1. And this is now our matrix P, which you can see that illustrated right down here. All right, so what have we done so far? Remember, we're trying to find this diagonalization. A equals P D P inverse. We found P first. We did that by looking for the eigenvalues. Then the second thing we did is we looked for the eigenvectors. The eigenvectors help us find this matrix P. So the third and final piece of the enchilada is going to be this P inverse right here. This is third. How do we find P inverse? Well, it's just the inverse of a matrix we now have in front of us. So we calculate the inverse of this matrix. Well, the idea is if we know what P is, we can augment this with the identity. So I3 right here. This will row reduce to the identity I3 and P inverse. This is our inversion algorithm. We're just going to utilize that in this context right here. And so that's exactly what you see right here. P augment the identity. And so if you go through the row reduction, we have a pivot in the first position. So we want to zero out the entries below it. We can take row 2 plus row 1. We can take row 3 minus row 1. That's not so bad. We're going to add 1, minus 1, minus 1, plus 1. We're going to minus 1, plus 1, plus 1, and minus 1 right there. So you see how these things change for the next matrix. The second and third rows will adapt as well. We then move on to the pivot position right here, which for that pivot we want a 1. So easiest way to fix that is just to switch rows 1 and 2. 2 and 3, excuse me. So looking at the pivot now, we already have a 0 below. We could try to zero things out above, but we'll just do it. We'll do standard Gaussian elimination here. So move on to the third column. You have a 1 in that pivot position. That's great. Let's get rid of the entries that are above. So we're going to take row 2 minus 2 times row 3. That gives us minus 2, plus 2, plus 2, and then nothing there. You don't have to do anything when there's a 0. And then we need to take row 1, and we're just going to add to it row 3. So we get plus 1, minus 1, minus 1. If you combine those terms, you will then get the matrix over here. We then move our pivot back to the second column. We want to get rid of that negative 1 that's in front. So we should take row 1 just plus row 2. So we add 1, add 1, add 2. And then we got the identity matrix right here. And this matrix on the side is our P inverse, which is computed by the usual algorithm of inversion. So we now have our inverse matrix given right here. If we have any doubt, we could actually multiply the two matrices together just to check that it equals the identity. But I think I'm going to skip that for now. And so now we have our diagonalization of the matrix. A is equal to P, D, P inverse with the three matrices that we have in front of us. So things to remember, the diagonals of D are our eigenvalues, 1, -2, -2. The columns of columns of D correspond to their eigenvalues. So 1, -1, 1 is an eigenvalue for negative or for positive 1. -1, 1, 0 is an eigenvalue for -2. And then we also get that -1, 0, -1 is an eigenvalue for -2 as well. So the order that you put the eigenvectors in P needs to match up with the order of the eigenvalues you put in the matrix D. And then the P inverse there, that is going to be that's just going to be the inverse of P right there. You could also think of it in terms of the row vectors are the row vectors of this matrix are eigenvectors or left eigenvectors and things like that. I don't necessarily want to go into that long discussion because we do have, the eigenspace is a null space of the matrix. You could also look at the left null space of certain matrices and you could get row eigenvectors. And so these guys are going to be row eigenvectors as well. I guess I should color code it better. I would recommend just finding this by the inversion algorithm, but this right here is a row eigenvector for 1. You'll notice, we don't need to get into this right now. You can check it yourself. If you multiply these matrices on the left, you'll see that these things are row vectors. And so there's this wonderful symmetry that comes from these matrices and their eigenvectors and eigenvalues. It's really kind of fun when you put all this stuff together. All right, and so that brings us to the end of our video. Thanks for being here, everyone. I guess I can't. I gotta say it. It feels like a sneeze I need to blow out here. If you take the P inverse, right? The vectors of the P inverse, they give us row eigenvectors, so left eigenvectors. So if you take 1, 1, 1, and you times it by the original matrix A, remember, which is 1, 3, 3, -3, -5, -3, 3, 3, and 1. If you multiply this thing through using the vector on the left, you take the first column, the dot product there, you're going to end up with a 1 minus 3 plus 3. If you take the second column, you end up with 3 there, minus 5, and plus 3. like so. And then for the last one, you kind of have to squeeze it in there. You're going to end up with 3 minus 3 plus 1. If you simplify all those, notice you end up with 1, 1, 1, which is equal to 1 times the vector 1, 1, 1. So this is a left eigenvector right there. Let me just do one more example with this. If you take the vector 1, 2, 1, and you times it by this matrix A, like so. When you multiply these things together, again by the usual rules, you end up with 1 minus 6 plus 3. It's the first spot. Then you're going to get 3 minus 10 plus 3, the second spot. And then for the last one, you end up with 3 minus 6 plus 1, like so. And if you simplify these quantities, you end up with, well, you're going to end up with negative 2 for the first entry. 1 minus 6 is 5 plus 3 is negative 2 there. Then for the next one, you're going to end up with negative 4. And then for the last one, you end up with negative 2 again. And if you factor out the negative 2, you end up with 1, 2, 1. So what I'm trying to say here is that the columns of P will be the eigenvectors of the matrix in the same order as the eigenvalues are listed in the diagonal matrix. But when it comes to P inverse, the rows of P inverse will be the left eigenvectors of our matrix A, and they'll also correspond to the exact same eigenvalues right there. It's just kind of like a fun little symmetry argument going on with this diagonalization process here. So all right, for Rizzle this time, we're going to end this video, and this ends section 6.3. This whole enchilada takes a long time. I'm looking at the video. We're sitting around 20 minutes right now on one exercise. But it takes a lot to develop the eigenvalues, to find them to eigenvectors. You don't need to find the left eigenvectors because you can just inverse the matrix, and that'll get them for you automatically. I hope this example is useful for everyone. If you have any questions, please post them in the comments below. If you like this video, please click the like button, click subscribe, so you can see cool videos like this in the future. And I'll see you next time, linear algebraians. Have a great day. Bye.